Hey everyone, welcome back to the Explainer. Grab those console cables, because today we're jumping directly into the Cisco command line. In our last Explainer, we covered the theory, we talk about what NAT and PAT actually are, how NAT translates addresses, and how PAT lets a whole bunch of devices share just one public IP. But let's be real, theory is only half the battle. Today we're going to configure them like actual network engineers. We are going step by step through a practical implementation. Okay, here's our roadmap for today. Router interface setup, static and dynamic NAT, PAT configuration, port forwarding rules, and finally, verification and troubleshooting. Think of me as your over-the-shoulder mentor for this one. Let's dive in. Section 1, Router Interface Setup, Defining the Boundaries. Look, before we can translate absolutely anything, the very first step is telling the router exactly which side is our internal network and which side is the external, public internet. Let's take a look at our setup. Over on the inside LAN, we've got a private network using the 192.168.1.0 subnet. That's hooked up to our router's Gigabit Ethernet 0/0 interface. Then, for our outside public network, we're on the 209.165.200.224/27 subnet running off Gigabit Ethernet 0/1. You're going to want to keep these interfaces in mind because they are literally the foundation of everything we're about to build. So let's see what this looks like on the CLI. First up, we drop into global configuration mode and hit our inside interface with interface Gigabit Ethernet 0/0. Next, we assign that internal IP address. IP address 192.168.1.1, 255.255.255.0. Now, pay close attention to step 3 right here. IP NAT inside. This little command is an absolute game changer. It officially flags this interface as the inside boundary for our NAT translations. Throw in a quick no shutdown to bring the interface up, and we're good to go. Right, now for the outside boundary. We jump into interface Gigabit Ethernet 0/1. We give it its public IP address with IP address 209.165.200.225 and a subnet mask of 255.255.255.224. And right there in step 3 is the exact counterpart to what we just did, IP NAT outside. Finish it off with no shutdown. Okay, your router now knows exactly where the private network ends and the wild west of the public internet begins. Moving right along to Section 2, Static and Dynamic NAT, the foundation of translation. Now that our boundaries are totally set, let's start creating the actual translation rules, and we'll kick things off with the most straightforward forms. Static NAT is, well, it's super simple. It just creates a permanent one-to-one mapping. So if you've got a private device, maybe a server, at 192.168.1.10, and you want it fully mapped to the public IP 209.165.200.226, you'd use this exact configuration. IP NAT, inside source, static 192.168.1.10, 209.165.200.226. It's direct, it never changes, and it's absolutely perfect for servers that need a totally consistent external identity. But what if you have a whole group of users who just need temporary outbound access? You don't want to map them all permanently. That's exactly where dynamic NAT steps up, and it's a really clean 3-step process. Step 1. We create an access list. Something like access list 1 permit 192.168.1.0.0.0.255. This tells the router which internal devices are actually allowed to be translated. Step 2. We define a pool of available public IPs using IP NAT pool. And finally, step 3. We tie the whole shebang together with IP NAT inside source list 1 pool public pool. What this does is automatically hand out a public IP from that pool to an internal device the second it needs to talk to the outside world. All right, Section 3, PAT or NAT Overload configuration, scaling the network. This is where things get incredibly practical, because honestly, this is the most common deployment you're going to see out there in enterprise environments. Let me pose a direct question to you. How do multiple internal devices share one single public IP address? Think about it. With dynamic NAT, you need one public IP for every private device communicating at that exact moment. If we did that for everything, we'd run out of public IPs almost instantly. No way that scales, right? Well, port address translation, or PAT, is exactly what solves this challenge. And the secret to pulling this off comes down to one absolute magic keyword in the Cisco iOS: overload. Literally, just adding this single word transforms your standard NAT into PAT. It allows thousands of internal devices to basically masquerade behind just one single public IP by utilizing unique port numbers for each session. Here's what that syntax actually looks like.
Just like before, you build an access list to define your inside network. From there, you've got two options. You can overload the outgoing interface directly by typing IPNAT inside source list 1 interface gigabit Ethernet 0/1 overload. This just grabs whatever IP is currently sitting on that external interface. Or if your company owns a specific block of IPs, you can overload via a pool with IPNAT inside source list 1 pool pat pool overload. Either way, it all hinges on throwing that vital overload command at the very end. Let's shift gears to Section 4, Port Forwarding Rules, Exposing Internal Servers. Up until now, we've really only talked about inside devices reaching out to the internet. But what happens when external traffic actually needs to reach inside to a specific machine?
Picture the scenario. You've got a private web server sitting safely inside your network at 192.168.1.100. But the public needs to access the website you're hosting on it using standard HTTP, which we all know runs on port 80. So, how do we let that outside traffic securely punch a hole through our router to that one specific internal server? The answer is port forwarding, which is really just a highly specific flavor of static NAT. The key here is how the port numbers just slot right into the command. For HTTP, we type IPNAT, inside source, static TCP, 192.168.1.180, 209.165.200.22680. See what we did there? We aren't just mapping the IP, we're mapping the exact TCP port. If you wanted to secure it with HTTPS, you'd simply swap those 80s out for 443. Got an FTP server? Drop in port 21. It gives you this amazing surgical precision over exactly what external traffic is allowed inside. Okay, Section 5, Verification and Troubleshooting, Proving it works. Honestly, any networking student can blindly type commands, but a real engineer knows how to verify their work and fix things when they inevitably go wrong. When you run your verification, you're going to be looking at a translation table exactly like this. Now, the inside local is your device's actual private IP and port. For example, 192.168.1.10 hitting port 1025. The inside global, on the other hand, is the public IP and port that the rest of the outside world sees. So, 209.165.200.225 on port 1025. Trust me, this table is your absolute best friend when you need to confirm that your translations are actively firing off. To actually pull up that table, you use the command show IPNAT translations. You can also keep an eye on your overall hit counts and misses by running show IPNAT statistics. If something feels off, always verify your base setup with show running config. And if you ever need to just wipe the slate completely clean and drop all your active dynamic translations, simply run clear IPNAT translation asterisk. Now, if your NAT still isn't working after all that, don't just sit there staring at the NAT commands. Go back to basics, verify that your interfaces are actually up using show IP interface brief. Check your routing table with show IP route. This is a big one. Check your access lists with show access lists to ensure you didn't accidentally block the very traffic you're trying to translate. And finally, just run some basic pings and trace routes out to a known public IP, like 8.8.8.8 to test raw connectivity. All right, before we wrap up, let's quickly hit the tactical design best practices. These are what separate the beginners from the pros. First, absolutely always double-check that your inside and outside interfaces are defined correctly. Getting those backward is a classic mistake. Second, in almost every enterprise environment, you're going to rely on PAT to conserve those public addresses. Third, save your static NAT solely for servers that truly require constant external exposure. And finally, please document your address pools and verify your ACL rules before you ever hit deploy. There's a quote from our source materials that just hits the nail on the head. Proper implementation allows internal devices to communicate externally while conserving public IPv4 addresses and supporting scalable network design. That is the whole point. That's why NAT and PAT are absolute necessities. They are literally the lifesavers keeping the entire IPv4 internet running today. And there you have it. You now understand exactly how NAT and PAT are configured in real working networks. You've got the commands, you understand the structure, and you are totally ready to crush your next lab. But I want to leave you with a thought. If NAT and PAT were created primarily just to delay the exhaustion of our IPv4 addresses, what's going to happen to all these configurations when the world finally transitions completely to IPv6? Will we even need them anymore? Let me know what you think down in the comments.
Thank you so much for watching. If this explainer helped you untangle NAT and PAT configuration, please like this explainer, subscribe to the channel, and turn on notifications so you don't miss our future networking lessons. Keep practicing those commands, and I'll see you in the next one.